Good morning, we are SiaA Sub-Orbitals. My name is Jackie Tran and I am the Project Chief Engineer. Richard is the SpaceShipTwo Chief Engineer and SK is the WhiteKnightTwo Chief Engineer. We will be analyzing Virgin Galactic's WhiteKnightTwo and SpaceShipTwo. There are 5 main mission requirements. These include to determine the feasibility and achievability of space tourism, to reverse engineer the WhiteKnightTwo and SpaceShipTwo, to ensure safety of the passengers, to highlight market competitiveness, and to verify our results with surrogate aircraft data. Our team consists of 21 members and is split among 8 different disciplines as shown on the left. A detailed project timeline for our team is shown on the right. I will now pass it on to the SpaceShipTwo Chief Engineer, Richard.
The purpose of SpaceShipTwo synthesis discipline was to create a methodology so that SpaceShipTwo could be analyzed. A literature review was performed to identify methodologies that could be used. Hypersonic convergence was selected for this methodology. Next. In the first multidisciplinary analysis, the design point for the vehicle was selected using hypersonic convergence. Next slide. The configuration layout further refined this model so that the next MDA, next slide please, configuration evaluation could be performed and the design point selected could be analyzed to ensure the criteria were met by the vehicle. Next slide please. The results for the parametric sizing can be seen here. The hypersonic convergence model that was created was verified using SpaceShipTwo. The model was able to accurately match the planetform area and takeoff gross weight of SpaceShipTwo, although the volume created by the model was higher than that of SpaceShipTwo. I'll now hand the presentation off to Will for SpaceShipTwo Weights.
An IDA methodology was derived and the references shown were used in the analysis. Next slide. The initial gross weight estimation was based on a correlation of similar vehicles. Using calculated weights of components and geometric values, the center of gravity was determined in 3 flight conditions: full, empty, and feathered. The center of gravity shifts aft during the flight due to the location of the fuel tanks, and then shifts forward when in feathered position, which puts the center of gravity at apogee in line with the roll thrusters. Next slide. Using aerodynamic data, a VN diagram was constructed. A 5-spar wing structure was selected and ceramic composite material with silicon carbide matrix and reinforced with carbon fibers was chosen. Finally, a thermal protection system was applied to the highlighted areas that experience high temperature during descent. Next is Garrett Tucker.
Here is a selection of my chosen literature as well as my personal IDA. Next slide. The process used to create the geometric model was a SolidWorks model was created, which then allowed me to pull the geometric values that were necessary for the creation of a VSP model, which was then pulled back into SolidWorks, which allowed me to find values such as the volume and the surface area. This method was confirmed using values from the space shuttle using the same method. Next slide. Here's a selection of my results from my geometric model, and I will pass it on to Josue for aerodynamics.
Thank you. These are the main sources we use to derive our analysis methodology as well as our IDAs. Next slide, please. Based on the process outline on the IDA on the right, we were able to derive these subsonic results. So overall, for Mach number effects, we saw a small increase in CO max and a small decrease in CD naught. Next slide, please. As far as altitude effects go, we saw a significant increase in CD naught and also a significant decrease in LVD max, which this factors into the descent analysis. Next slide, please. Here we have the load distribution diagram on the left, where we saw that the horizontal tail will actually stall past 25 degrees of alpha. And over on the right, we have the static margin, which we were able to confirm will stay positive for all CG locations. Next slide, please. Our key results overall were a fully defined aerodynamic data set for the entire vehicle flight envelope, as well as satisfactory results from the other disciplines analysis based on our aerodynamic data. And now I'll hand it over to Jared.
Thank you. The IDA on the right was used to produce the results shown here. They are correlated with Mach number as expected using the supersonic theory. Next slide, please. The drag divergence Mach number was found to be 1.1, and it drops quickly after 1.2. This did not exceed any of the thrust limits provided to us. Next slide, please. Through the feathered descent, there is a wide variation in it because of the method by which it descends. There's a heavy correlation between Mach number and angle of attack with drag, but altitude not as much. So through the long period deceleration, thermal effects were relatively on par with nominal thermal effects. Next slide, please. The key results are an supersonic A load distribution is also available through VSP data, and satisfactory results were found through the flight envelope. I'll be passing it off to Thomas.
Thank you, Jared. First and foremost is the primary literature used to aid in the rocket analysis IDA. Next slide. The primary objective of the propulsion system is to provide enough thrust for its ascent portion of the trajectory. SpaceShipTwo uses a hybrid rocket motor consisting of nitrous oxide and HTPV. It was assumed that SpaceShipTwo used a similar chamber pressure as SpaceShip1. This value was used in the NASA SiaA code at a nominal OF ratio of 5.5. Table on the left shows the initial design choices. Next slide. Using the thrust required and initial specific impulse, the mass flow rate required was determined. Additional sizing properties can be seen on the left table. The 4-port wagon wheel used for SpaceShip1 was also chosen for SpaceShip2. The right table includes a regression rate as well as the initial and final port geometries. Next slide. With an allowable OF ratio of 5.5 to 6.5, performance parameters were reiterated with the max thrust and specific impulse of 256 kilonewtons and 300 seconds respectively, satisfying the mission requirements and geometric constraints. The analysis was verified with the liquid oxygen and polybutadiene hybrid engine at a nominal OF ratio of 2.1. Thank you. I will now hand it off to Henry.
Thank you, Thomas. The literature review for the trajectory and performance methodology is now being illustrated. Next slide. Using the energy state approximation method for the power ascent, the trajectory verification came from Bryson's airplane B and Chidobe and Huang's rocket plane XP. The magnitude deviation is due to uncertainty in aerodynamics and propulsion parameters. However, the convergency of the trajectory behavior should be remarked. Next slide. The trajectory verification of the empowered coast projectile motion came from a simulation software from the University of Colorado. Next slide. The power ascent behavior of SpaceShip2 is now being illustrated. The maximum Mach number experienced was 3.55 with a load factor of 2.4 and main engine cutoff at 41 kilometers. Next slide. The unpowered coast behavior is now shown to the left, while the complete climb trajectory of SpaceShip2 is now shown to the right. The apogee of SpaceShip2 was of 103 kilometers. Next slide. The power ascent trajectory was used for determining the performance characteristic of SpaceShip2, shown on this slide and on the following slide. I will now be passing this presentation to Justin Ryan.
Hello, I'm Justin Ryan, and this is the verification of method and IDA pertaining to reentry. Next slide, please. After verifying the method, team inputs were processed and a maximum of 4.94 Gs, a Mach number of 3.17, and a flight path angle of 90 degrees was experienced. Next slide, please. Various vehicle aerodynamic data was used for verification and calculated their subsequent performance characteristics. Next slide, please. Based on data provided by the aerodynamics team, a time to descend to an appropriate altitude for landing took 17 minutes and 44 seconds with a final glide velocity of 78.53 meters per second. Next slide, please. Verification and IDA data is presented and shows strong correlation for the Space Shuttle and Hope vehicle. Next slide, please. Based on SpaceShipTwo geometry, a 90-degree angle of attack should be used for landing. This will require a minor dip into a steeper glide slope, utilize 20% of Spaceport America's runway, and decelerate at a reasonable pace. I'd like to hand off to Benjamin Ship for stability and controls.
Thank you, Justin. Provided here are the references used in the development of the IDA. Next. SpaceShipTwo's neutral point was determined by varying the CG fore to aft as approximately 10 meters aft of the nose. This provided high static margin for takeoff gross weight and low when empty. Horizontal tail sizing was verified with estimates based on the surface area of the tail booms. Next. The safety of the spacecraft was verified as the longitudinal stability derivative Cm alpha was found to be negative in all normal configurations, flight regimes for both empty and takeoff gross weight. Subsonic is shown here. Next. And supersonic presented here. Next. Here, Cm alpha trend to a Mach input was verified to show normal behavior. And finally, the thrust required for pitch control in low or no atmosphere is presented as a function of the estimated pitching moment of inertia. Up next will be Jackie with the lateral and directional stability.
Thank you, Ben. This is the lateral directional stability literature review and IDA. The literature review is primarily focused on methodologies outlined by Roscom, Yuckout, and Phillips. This is the verification for the methodology with the X-15 as a surrogate aircraft. Although these results seem a bit off, the magnitude is extremely small. Since this is only an approximation, I believe that this fits the big picture pretty well. There are three main points that I analyzed: separation, feather descent, and glide. The results after release are shown on the right. CN beta is positive and CL beta is negative, which meets the static stability criteria. For re-entry, we can estimate that it becomes unstable at around 80 degrees angle of attack. Otherwise, it is stable. The glide results also satisfy the static stability criteria. In conclusion, SpaceShipTwo will be statically stable throughout its flight profile. I will now pass it on to Brian.
Thank you, Jackie. As can be observed, the commercial space industry is expected to have an economic boom over the next 2 decades. In suborbital space tourism, there is an interest not only for individuals, but for enterprises as well, showing that there is a substantial market. Next slide. The main methodology used to perform the cost analysis was Corley's trans-cost model. This allowed for the development, manufacturing, and operating costs to be calculated as shown on the next slide. The calculated development cost of $1.2 billion and operating cost of $404,000 were verified with documents published by Virgin Galactic. Meanwhile, the manufacturing cost was verified by data from the X-15. The relatively low percent errors validate the calculations performed with the trans-cost method. Next slide. With the learning curve, the manufacturing costs of each subsequent vehicle decreases exponentially. As a result, the company is able to achieve a profit within 2 years. This analysis proves that the Virgin Galactic model is a financially viable method for suborbital space tourism. I'll now pass it back to Richard.
From our analysis, we were able to determine that the SpaceShipTwo vehicle would be able to safely take passengers above the Kármán line while also becoming profitable in the near future. I will now pass it off to SK to discuss the WhiteKnightTwo synthesis discipline.
Thank you. As the chief engineer, I was responsible for creating the MDAs for the WhiteKnightTwo team by analyzing each and every flight condition in the flight system in order to include the parameters in the MDA. In this slide, you can see the parametric sizing MDA for the WhiteKnightTwo team and the condensed literature review used for this phase. Next slide. After creating the parametric sizing MDA, the configuration layout MDA was created to carry out trade studies for exploring different design points residing in the solution space, as well as to verify the sizing process. Next slide. The configuration evaluation MDA was then created to provide a guideline for in-depth analysis of the selected design point with inputs coming from all of the disciplines. A market analysis was developed to calculate the overall composition of the vehicle. Next slide. The solution space for the WhiteKnightTwo was generated by calculating its performance during different phases of its mission and keeping the federal aviation regulations in mind. The effects of different high-lift devices were also included in this study to provide subsequent data. Next slide. After creating an initial solution space, data from a surrogate aircraft was used to calculate another solution space to verify the process of this study. The Boeing 737-900ER was used specifically for this study due to the availability of data to the public for this aircraft, and the comparison can be seen in this slide. Now I'll pass it over to Alejandro.
Thank you, SK. The disciplinary analysis began with the literature review. Next slide. With the literature review, methods were selected and were verified using published data for the Boeing 747 launch. Next slide. Using the verified methods, the weights of the components of the WhiteKnightTwo were calculated. Next slide. The weight at each flight phase was calculated and plotted to show the change in weight of the aircraft during its mission. Next slide. The location of the center of gravity of each component was found. Measurements from those center of gravities to the leading edge of the wing were taken. Next slide. With this data, the center of gravity for the whole aircraft in different configurations and during different flight phases was determined and plotted. Next slide, please. The structural analysis involved making a material selection. The material chosen for the structure was a carbon composite. Next slide, please. The structural analysis also involved a V-in diagram to create a V-in diagram to understand the critical load cases, and the structure of the fuselage and wing was found. I'll now pass it on to Jen.
Thank you, Alejandro. The geometry discipline plays a significant role in the story we tell of reverse engineering the WhiteKnightTwo. The majority of the work done by the geometry team gives a cogent outline of the configuration layout phase, such that the rest of the disciplines may carry out their configuration evaluation. Consequently, a brief highlight of the literature review references is shown here, the geometric determination process IDA used. Next slide. As a result of this process, the primary geometric data for the lifting surfaces and the fuselage of the WhiteKnightTwo are shown below. Prominent parameters found include a main wing aspect ratio of 15.1, mean aerodynamic chord of 8.08 feet, and various planform areas. Next slide. The aforementioned data are verified via the conduit of a validation process by which the Boeing 747-200's known geometric values are run through an iteration of the geometry code developed. This process yielded relatively low error margins, averaging between 0 and 10% across the board. Next slide. This data led to the development of computer-aided design models in both VSP Aero on this slide, and on the next slide, we have a SolidWorks model shown in 3-view and isometric format. A 3D printed scale model was made from these files as well. Next slide. The integration of both the SpaceShipTwo and WhiteKnightTwo also imposes some design constraints on one another. This includes strength of the middle wing to hold the SpaceShipTwo, height of the pylon at 11.2 feet, clearance between both fuselages of 52.4 feet, and more shown below. Thank you. I would now like to introduce Luke Patterson.
Thank you, Jenner. For the WhiteKnightTwo aerodynamics of tandem flight, the aerodynamic properties of takeoff, climb, and cruise up until separation had to be evaluated. Next slide. This is accomplished through the Sub-Orbital's tandem flight aerodynamic software toolset based on the methodology derived from literature review. Importing the full geometry and flight condition information for both vehicles allows for the full calculation of total tandem vehicle drag and lift. This data is then exported and compared with VSP Aero predictions. Next slide. During the takeoff run, the combined vehicle begins increasing its drag and lift before it reaches maximum lift-to-drag ratio of 12.9 on liftoff and begins its ascent to 50,000 feet. Next slide. During the climb phase, the vehicle aerodynamics were evaluated based on the flight condition information provided by Trajectory and Performance. The vehicle takes on the most drag at 10,000 feet before falling below drag at takeoff. Next slide. Finally, calculations are made for WhiteKnightTwo at cruise and maintains a lift-to-drag ratio of 8.2 at 1.5 angle of attack. Now, I'd like to pass it to Justin.
Thank you, Luke. The literature shown was used as a reference to develop the methodology of the analysis. The methodology for the descent and landing phase follows a standard subsonic aircraft analysis where emission requirements and geometry constraints were input into a numerical analysis program, with the output being the aerodynamic coefficients of the aircraft in this part of the flight envelope. These coefficients are of interest to the performance discipline so they can conduct further analysis of the landing and performance characteristics. Next slide, please. For the descent phase, I did a sweep of analysis across the flight envelope from the cruise Mach to the approach phase of flight, from Mach values of 0.55 to a little less than 0.2 Mach. As can be seen by the plots on the slide, the aircraft performs with typical aerodynamic characteristics of a typical subsonic aircraft, with its double fuselage configuration not interfering significantly. As expected, the aircraft saw extreme efficiency in the lower angles of attack, with L/D max of this phase being around 4 degrees with a value a little over 28. This indicates a more than acceptable aerodynamic efficiency of the aircraft as it makes its return flight into approach for landing. And now I'll pass it on to Miguel Navarro to talk about propulsion.
Thank you, Justin. This slide shows my literature review and the developed IDA. Next slide, please. The first step was to create a code that will help analyze the data. Using Madeline's formulas, the code was created and was tested by recreating the graphs found in the book. This code is then used with the DC-10 and Boeing 747 with the highest percent error of 2%. Next slide, please. Using the code, the uninstalled properties of the PW308A are shown on the slide. The graphs details the thrust, specific fuel consumption, and power versus Mach and altitude. The result shows that the uninstalled PW308A is a capable engine for the White Knight. Next slide, please. Drag obtained from aerodynamics is used to calculate the installed thrust shown here. With the installed drag, the other uninstalled properties are found. The installed properties pass the required thrust and power performance. Next slide, please. A study to see if the best engine was conducted, and Virgin Galactic did not use the best engine. Out of the 4 similar engines, the AE engine was the best. I'll pass it on to Pravasha to finish up propulsion.
Thanks, Miguel. It is quite clear by now the results obtained for installed and uninstalled thrust from my colleagues' data. Engine data analysis on my part starts when SpaceShipTwo detaches from WhiteKnightTwo. Most of my parametric cycle analysis were conducted using Mattingly and Nicolai's approaches. Next slide. Shown is a table of collected data through the literature review process containing performance parameters of various mid-range turbofan engines. Next slide. The results presented during the descent phase include specific thrust and specific fuel consumption are shown, which serve as a key factor in determining the efficiency of a mission. Next slide. The methodology that was developed for this analysis needs to be tested and verified to be considered as an appropriate reverse engineered model. First, I started off with verifying the data obtained for component performance characteristics, which was referenced with that of Mattingly's plot. Then I moved on to calculating mission control parameters, which I verified then with LOD rules, turbofan and turbojet engine handbook of the specified surrogate engines. Next slide. Moreover, the MATLAB code results were verified against Mattingly software to further solidify the accuracy of the results and the matching to that of the actual Pratt & Whitney 308A engines. Overall, the thorough analysis proved that the WhiteKnightTwo was equipped with acceptable engines to power the mission. Next is Pablo to present to you with trajectory and performance results.
Hi, this is a literature review that was used to conduct the trajectory and performance of the WhiteKnightTwo. Next slide. The takeoff phase was conducted using Roscombe's method following the FR25 requirements. The power required and thrust required were able to be calculated using the information from weights. Next slide. The energy state approximation method was used for the climb of the phase of the WhiteKnightTwo. The method was able to approximate the velocity and weights at each of the altitudes of the climb, and having the flight trajectory profile, the thrust required and power required were able to be attained at each of the altitudes, including such thing as the rate of climb. Next slide. A steady state flight was assumed for the WhiteKnightTwo at cruise after the separation point. This allowed me to relate the power required and the power available, similar to the thrust required and the thrust available. The load factor was also found for maneuverability purposes of the WhiteKnightTwo. Next slide. This descent phase was also used the energy state approximation method as well to find the flight trajectory profile. Thrust required and power required were also found using this method. Next slide. The landing phase analysis followed the FR25 requirements and considered the velocity approach and the weight of the WhiteKnightTwo at this phase. The power required and thrust calculation were also shown and verified with the propulsion team and aerodynamics team for the entire mission profile. Now passing it on to Gabriel Reyes for the stability and control.
Thank you. Here's my literature review and IDA for stability and control. Next slide. The figure on the left shows the coefficient of pitching moment varied against angle of attack. The tail provides the biggest contribution to longitudinal stability. The total aircraft contribution is shown to be statically stable with a negative CM alpha slope. The right figure shows the reduced order model of the WhiteKnightTwo, showing the center of gravity and neutral point positions. Next slide. Shown in this slide is the control surface sizing for the WhiteKnightTwo. The two figures show the horizontal and vertical tail areas. Also on these figures are various horizontal and vertical tail volume coefficients shown in the legend. Next slide. Shown in these two figures is the directional and lateral static stability for the WhiteKnightTwo for climb varied against Mach number. The directional stability is plotted for various quarter chord sweeps ranging from 0 to 45 degrees. The lateral stability is plotted for various wing dihedrals ranging from 0 to 60 degrees. Next slide. Shown in these figures are the directional and lateral static stability for steady cruise. C and beta is positive for climb and cruise. Up next is MOES with cost market.
Thank you. To begin the cost analysis process, Rester, Nikolai, and Raymer's literature was primarily researched. Using this information, an individual cost estimation methodology was developed and used to calculate the development cost, maintenance costs, and operation costs. Next slide, please. An estimated $427 million was spent on developing the WhiteKnightTwo, with an estimated $100,000 mission operation costs. Using this data, it is estimated that the company will break even after 535 flights, which is estimated to occur by the year 2022. Next slide, please. Verification data was obtained from Virgin Galactic's Investor 2018 and 2019 presentations. Next slide, please. Our main competition in the suborbital space tourism market is Blue Origin. However, Virgin Galactic offers a safer, more comprehensive customer and flight experience, and is a better validated program with over 600 plus tickets sold. Now I'll pass it back to SK.
Thank you. After concluding this study, it was found that the geometric models were able to provide the parameters required for results with low error margins. The WhiteKnightTwo was observed to carry out its mission, which was to get SpaceShipTwo to a suitable separation altitude, and the team was able to understand the key aspects of the engineering decisions utilized during the design phase of this vehicle. It was also concluded that Virgin Galactic may run into trouble with its close competitor Blue Origin, but a better customer experience program may give Virgin Galactic the silver lining they're looking for. Now I'll pass it over to Jackie.
Here is our 3D printed models. I would like to thank Luke Patterson for printing this. I think they turned out pretty great. And this concludes our presentation. Thank you for listening.
Good morning, everyone. My name is Cody Harris, and welcome to StarQuest Capstone Senior Design Presentation. The objective of this project was to reverse engineer the Virgin Galactic two-stage space tourism system and perform a cost analysis on the feasibility of the design. A set of teams has been put together to complete this project as shown. The analysis can be broken down into three main sections: parametric sizing, configuration layout, and configuration evaluation. With the given mission requirements, each vehicle will be sized to match information known about the system. Next, this data is passed into geometry to perform the configuration layout to match the layout utilized by Virgin Galactic. Lastly, geometry sends this information into the configuration evaluation, where each discipline performs calculations and passes data to other disciplines. After all the calculations are complete, a conclusion is reached to determine if the system is a feasible design for the mission. Before we get into sizing, Bree and Vittorio will start with a competition analysis to show what WhiteKnightTwo and SpaceShipTwo are competing against.
Good morning, my name is Brianna. The mission for market analysis was to determine the viability of the WhiteKnightTwo within the space tourism market and find other means of service for the aircraft. Using parametric methodology for market analysis, I chose 5 aircraft that had previous use as horizontal to launch vehicles with varying parameters and captive or carry configurations. These allowed for better understanding of capabilities needed for horizontal to launch vehicles. Analyzing the principal variables of these 5 aircraft and launch vehicles determined the type of market for WhiteKnightTwo that it was created for and outlined the aspects that mattered in design, mission, sizing, and cost. Next slide, please. For competition analysis, the 4 main competitor companies and their vehicles were researched to understand the competition and the challenging vehicle potentials. Company press releases were followed continuously to obtain any updated information of the vehicles, development schedules, and launches. Next is MAE with SpaceShipTwo Market Analysis.
Good morning. For market analysis, I answer why there is a market and demand for space tourism and how Virgin Galactic and their mission fit in the picture, which ties in with the objectives of cost analysis. Next slide, please. I gathered important data for SpaceShipTwo and highlighted the mission in order to create a better understanding how and where Virgin Galactic stands among its competition. Next will be Jason with the WhiteKnightTwo synthesis.
Good morning, everyone. Synthesis is a discipline that deals with sizing the vehicle to a converged takeoff gross weight and planform area and forms a methodology that processes the entire conceptual design phase. The WhiteKnightTwo in this case is broken down into 3 phases as shown below, where synthesis mainly quantifies the parametric sizing portion. The mission requirements are shown, where the WhiteKnightTwo is designed as a carrier vehicle for various payloads. Next slide. To verify the hypersonic convergence approach that was utilized, data from the actual WhiteKnightTwo with the mission occurring SpaceShipTwo is utilized, along with an additional reference twin fuselage vehicle to show that the results obtained make sense. The white area in the plot is feasible design space where the wing loading requirements are met. Next slide. Results obtained from the synthesis discipline for WhiteKnightTwo include a carpet plot of increasing payload to the max stated payload of 17,000 kilograms, with the location of the WhiteKnightTwo and another twin fuselage vehicle indicated on the plot. The significance of this is that the vehicle is verified to work and is not a hoax. Cody will now discuss the synthesis of SpaceShipTwo.
Thank you. The sizing of SpaceShipTwo utilizes hypersonic convergence due to it being a high-performance supersonic vehicle. Utilizing the 2-stage orbit set of orbit equations from the Van de Graaff and adjusting sizing parameters to represent SpaceShipTwo, the planform area and takeoff gross weight are able to converge where the percent errors are minimal. For the combined system, hypersonic convergence was utilized to size both vehicles, again using the 2-stage orbit equations. Adjusting the sizing parameters, each vehicle has a converged planform area and takeoff gross weight with minimal percent errors compared to the values of the real vehicles. With sizing complete, I pass it on to NK for WhiteKnightTwo Geometry.
Thank you. The overall purpose of the geometry discipline is to define the geometrical values of the WhiteKnightTwo and SpaceShipTwo vehicles. These values are then given to other disciplines such as aerodynamics and structures for their own disciplinary analysis. The main objectives of focus for this semester are to create CAD models of both vehicles, create a completed list of geometrical variables, and determine the geometrical constraints both vehicles place on each other. The software OpenVSP was used to create the CAD model for WhiteKnightTwo. Shown on this slide is the final 3D CAD model and the geometrical values obtained from the model. Also shown are the approximate locations of the fuel tanks and passenger seating for the vehicle. I'll now hand it over to Christian for SpaceShipTwo Geometry.
Thank you. The SpaceShipTwo model was created using SolidWorks. On the right, you can see the CAD drawings that have been produced for both the feathered and unfeathered configurations. The top view on that top drawing shows an approximate location of the passenger seating, fuel and oxidizer tank, and rocket engine based on a schematic from the NTSB accident report. Also shown is the IDA for SpaceShipTwo Geometry and a table of some of the more significant geometric data, along with what were determined to be the maximum allowable dimensions or constraints for SpaceShipTwo to fit under WhiteKnightTwo during combined flight. Lastly, on the bottom there are a few demonstrations of the script that was written to scale the dimensions of SpaceShipTwo for synthesis. Now, with the geometry of both vehicles completed, the analysis of the flight phases of WhiteKnightTwo can begin.
Thank you, Christian. For the WhiteKnightTwo Propulsion discipline, an extensive literature review was conducted to obtain and review different methods on how performance measures of the 4 turbofan engines would be obtained. The selected method for the analysis was a modified version of real engine cycle analysis for a mixed-flow turbofan engine, and the engine selected from the database was the JT90 and CF6 turbofan engine, with errors less than 7%. This modified method obtained a takeoff thrust of 210 kilonewtons and continued through the flight trajectory to show the thrust-specific fuel consumption, mass flow rate, specific thrust, and overall engine efficiency before and after separation of SpaceShipTwo. Next slide. The same modified method was used during the landing flight phase, and all propulsion performance measures decreased all the way back down to Mach 0, where the WhiteKnight2 mission was completed. The analyzed power plants were able to meet mission requirements during each flight phase, and a maximum engine efficiency of 21.88% was obtained during cruise. Further study and optimization of the engine components will be conducted for the design portion. Next will be Ricky to discuss the weights and balance discipline.
The initial objective of the weights and balance discipline is to estimate the takeoff gross weight using historical data and tread lines of surrogate vehicles. The WhiteKnight 1, Global Flyer, and Rudin Model 76 Voyager were used to obtain a takeoff gross weight of 30,534.9 kilograms. A refined empty weight calculation is made using geometric parameters and empirical equations to determine the weight of major aircraft components. The pie chart illustrates the empty weight makeup, which totals to 13,617 kilograms. Adding payload, crew weight, and fuel weight presents a new takeoff gross weight of 28,712 kilograms, resulting in a 2.67% error. Next slide, please. Given the weights of each major component and a reference line at the nose tip of the aircraft, a calculated CG of 6.67 meters for the takeoff phase is obtained. The CG shifts backwards during the separation of SpaceShipTwo and landing phase. Next will be Johnny Gwynn with the aerodynamics discipline. Thank you.
The primary objectives of the aerodynamics team is to determine lift, drag, and the aerodynamic efficiency of WhiteKnight2. The wing was assumed to be uncambered due to minimal camber. Turbulent flow was assumed for more realistic results, and zero lift was assumed for SpaceShipTwo. The IDAs were also listed here. Next slide, please. The methodology was verified using the Global Hawk and the U2 as surrogates. The drag methodology had a maximum percent error of 11.42%. The methods were deemed acceptable. Jose Vasquez will now discuss the findings of the aerodynamics team.
Thank you, Johnny. One of the major assumptions made for the combined system was neglecting any lift contributed by the SpaceShipTwo aircraft. With this assumption, it was found that enough lift was produced for takeoff at approximately an angle of attack of 6 degrees. The lift and drag coefficients produced are listed here. The minimum required wing area for takeoff was estimated to be 114.77 meters squared. Next slide, please. Continuing with the assumption previously stated, it was found that in order for the combined system to fly at an altitude of 15 kilometers, the angle of attack must be approximately 5 degrees at Mach 0.6. The lift and drag coefficients produced are listed here. The minimum required wing area for the combined crews was estimated to be 112.43 meters squared. Next slide, please. At separation, the system experienced a significant decrease in drag and weight. It was found that in order for WhiteKnight2 to cruise at an altitude of 15 kilometers, the angle of attack must be approximately 2 degrees at Mach 0.6. The lift and drag coefficients produced are listed here. The minimum required wing area for WhiteKnight2 at cruise was estimated to be 111.76 meters squared. Next slide, please. The last flight phase of interest analyzed was the landing phase. It was determined that in order for enough lift to be generated at landing, WhiteKnight2 must land at an angle of attack of approximately 5 degrees. The lift and drag coefficients are listed here. It was found that the minimum wing area required for the landing phase was approximately 108.72 meters squared. Therefore, it can be reasonably assumed that WhiteKnight2 wing was sized for the takeoff flight phase. Now we'll pass it on to my colleague Glenn to discuss trajectory.
Good morning. In the trajectory and performance analysis, we used 5 primary texts to develop our methodology. These were verified using the Boeing 747-400 and the Lockheed TriStar, whose results can be seen in the table on the left-hand side. Next slide, please. With our verified methodology, fuel fractions were determined for each flight phase. While some values produced by this method yielded unfavorable results, the majority of the flight phases have reasonable values, and further research will be conducted next semester to calculate more accurate values for the takeoff and landing. Now to Tamana for performance analysis.
All the performance analysis was conducted assuming the launch site as Spaceport America. For a takeoff and landing analysis, many FAR-25 jet transport aircraft requirements were assumed. In combined vehicle performance, the takeoff velocity was determined to be approximately 69 meters per second after a ground roll distance of approximately 277 meters in order to allow a 50 feet of obstacle clearance distance. WhiteKnightTwo then enters the climb phase with a flight path angle of approximately 4 degrees. During separation, there is a significant difference to the flight performance of WhiteKnightTwo. The total range of the vehicle, calculated as the combined ranges of climb, both cruise phases, and descent, was approximately 82 kilometers. The total flight time of WhiteKnightTwo in combined and then post-separation flight is about 81 minutes, which is close within 5% of the literature values obtained for the system. Next will be David and Daniela with the Stability and Control discipline.
Determine if the vehicle's pitching moments are satisfactory and give the vehicle stable performance. The Boeing 747-400 was used for verification of the methods obtained from Roscom, Nelson, and Pamati. There was a simplification made to the analysis in order to effectively analyze the stability of the vehicle. Instead of a twin fuselage, the vehicle configuration was treated as a single, larger fuselage. For the longitudinal static stability, WhiteKnightTwo was satisfactory, but rather stiff at around a pitching moment of negative 2.0 per radian for the given center of gravity, and a static margin was large at around 40%. For the combined vehicle, the pitching moment was improved with the more aft CG at a pitching moment of negative 1.2 per radian, and the static margin was improved. I will now pass it on to Daniela with the lateral directional analysis.
When analyzing the directional and lateral stability of WhiteKnightTwo throughout its critical flight phases, the stability derivatives produced lie within a reasonable range, as the recommended yawing moment for a Mach number of 0 to 0.8 is 0.08 to 0.25 per radian range. The results calculated ensures that yaw stability throughout WhiteKnightTwo flight phases is met. The same can be said when analyzing the stability derivatives for roll. Graphs that were a result of the codes produced using the literature gathered also shows the individualized contributions to the total moment of the aircraft. Bree will now discuss WhiteKnightTwo's cost analysis.
Thank you. The mission was to determine the viability of the cost of WhiteKnightTwo. The objective was to become familiarized with methods and models used for cost estimation within the preliminary design phase and apply them to WhiteKnightTwo. This included calculating the life cycle cost, development and production cost, and direct operating cost. The 1967 Air Transport Association of America cost model for transport aircraft was used to determine the direct operating cost. The final costs were adjusted to 2020 values with inflation rates calculated from the U.S. Bureau of Labor Statistics. Next slide, please. For calculation, it was assumed to have a total of 6 spaceports with 1 operating WhiteKnightTwo at each. With production of 6 aircraft, a viable unit cost was determined. The goal of 400 flights per year per carrier vehicle, input from each discipline, was obtained to achieve suitable price. The cost analysis of the vehicle has concluded that the life and cost of operation are feasible for this aircraft considering a sustained economy where flight operations were conducted as normal without any delay. With this results and comparable prices to competitor vehicles, the vehicle is also market feasible within the space tourism industry using ticket prices between $250,000 and $300,000. This does not include revenue as a carrier aircraft to be privately used for the research at high altitudes, which would add to the profit. Nor does it include the analysis of the beginning of commercial hypersonic vehicles use that has the capability of replacing present vehicles within the space tourism industry. With analysis of WhiteKnightTwo complete, Kapil will begin SpaceShipTwo flight phase analysis.
Good morning, everyone. I'll be going through the propulsion system of the SpaceShipTwo. From the literature review for the methodology, mathematical modeling was used to model the rocket motor 2. For the mass property change, empirical method of curve fittings was used. Since the NASA SiaA codes use similar approach, they were used for obtaining the critical information of the liquid oxidizer N2O and solid fuel STPB. On the right hand side, you can see the results from the SiaA codes for the adiabatic flame ratio of the specific heats with burn time and the oxidizer to fuel ratio based on the adiabatic flame temperature. Also, the 4-port grain geometry of the solid fuel calculated based on the literature review and assumptions can be seen in the middle with the expected thrust profile for such geometry. Next slide, please. For the results, the thrust profile obtained can be seen on the top right hand side that matches our thrust profile prediction followed by the specific impulse profile. Also, we can see the mass flow rate of the propellants with time in the middle. We can see the moment of inertia change on the right hand side. On the bottom of the middle section, we can see the graph of the change of center of gravity's position with burn time. Finally, the tabulated results compare the obtained data with the known data for verification as shown for thrust as well as mass properties. They were well within the reasonable range for the known data. Next will be Sam with the SpaceShipTwo Weights and Balance.
Good morning. I will discuss the analysis for the weights and balance discipline of SpaceShipTwo. Using Roscom's trendline approach based on surrogate aircrafts, the estimated takeoff gross weight and empty weight of SpaceShipTwo are 9,403 kilograms and 5,524 kilograms, with a takeoff gross weight percent error of 3.54%. Using Raymer's corrected fighter aircraft empirical formulas corrected for the composite material selection of SpaceShipTwo, the takeoff gross weight and empty weight of SpaceShipTwo are 9,171 kilograms and 4,266 kilograms, respectively, with a takeoff gross weight percent error of 5.84%. The weight at the end of the boost phase is 6,024 kilograms using the trendline approach. Next slide. After the weight analysis has been completed and using Sedre's CG estimation method, the center of gravity of SpaceShipTwo at takeoff is approximately 7.21 meters, shown on the side view of SpaceShipTwo. At the end of the boost phase, after fuel has been depleted, the CG shifts forward to a value of 6.64 meters. Next will be Garrett with the Aerodynamics division.
Hi everyone, I'll be talking about the aerodynamic analysis of SpaceShipTwo. Examples of the lift calculations are shown on the left with varying Mach and angle of attack, and on the right you can see that the DATCOM and CUI methods used were verified using Space Shuttle surrogate vehicle data and found to have less than 10%. Next slide, please. Examples of the drag calculations are shown on the left along with the example drag polars constructed. On the right, you can see the Raymer method was verified using Space Shuttle surrogate vehicle data as well. Next slide, please. An aerothermal analysis was also conducted for SpaceShipTwo. On the left, you can see the heat flux and maximum temperatures experienced during a worst-case scenario reentry, and the full SpaceShipTwo aerodynamic analysis served as inputs for the trajectory and stability calculations. And now on to trajectory and performance with Jose.
The SpaceShipTwo is released from the WhiteKnightTwo at 15 kilometers. The propulsion system will then begin to burn. At a time of 11 seconds, a Mach number of 1 is reached. An engine burnout time of 64 seconds was recorded and a max velocity of 1,350 meters per second is achieved. A flight path angle of 84 degrees was chosen to ensure that an apogee value of 102.56 kilometers is met. Microgravity coast phase starts at 100 kilometers at the Kármán line, and the SpaceShipTwo will spend 3 minutes and 42 seconds in microgravity. Using data obtained by the propulsion, aerodynamics, and weights disciplines, a fuel fraction of 0.57 was calculated. Next slide, please. Re-entry phase occurs directly after the microgravity coast phase ends. A methodology adopted by Sanger and Hammond was used to calculate the values. Re-entry will range from 100 kilometers down to 22 kilometers. Shortly after the tail booms of the SpaceShipTwo are lowered, and the gliding phase starts, a max velocity of 1,000 meters per second is reached at a Mach number of 3.66. The max deceleration force that is measured for the SpaceShipTwo is 6.1 Gs. Next slide, please. An overall time study was done for the flight phases of the boost, microgravity coast, re-entry, glide, and ending with the landing on a horizontal runway. The flight profile of the SpaceShipTwo has a total time of 123 minutes. Next, I will hand it off to Javier with Stability and Control.
Morning everyone. For the longitudinal stability of SpaceShipTwo, the pitching moment coefficient increases as SpaceShipTwo travels through the power descent flight phase. Therefore, as its velocity increases, its pitching moment increases and it becomes even more stable at a value of negative 0.0381 per radian. As its neutral point shifts past 35% of the mean aerodynamic chord, its longitudinal stability increases as well. However, at high angles of attack for the horizontal control surface, there could be flow separation and its pitching moment slope becomes positive, causing instability to SpaceShipTwo. Next slide, please. One of the factors that affects the lateral stability of SpaceShipTwo is the height of the tail boom above the fuselage. So for the feather position during the apogee, the lateral stability of SpaceShipTwo is highly increased. Next slide, please. For the directional stability of SpaceShipTwo, we compared against the effects of side slip and determined that the yawing moment coefficient or weathercock stability is greater than 0, therefore stable for side slips angles between -10 and 10 degrees for the climb, glide, and landing phases. With this information, we determined that SpaceShipTwo meets the stability and control requirements. Next will be Vittorio with the cost discipline.
The life cycle of a vehicle is essentially in 3 phases, and the cost for the first 2 phases, development and production, I have chosen Nikolai's life cycle cost methodology. Next slide, please. For the operations phase, I decided to go with Coel's trans-cost model in order to obtain direct operating costs. Next slide, please. Here we see that the total development cost is about $2 billion, with airframe engineering and development support being the 2 largest contributors. Next slide, please. The total production cost is around $1.4 billion, with sustaining engineering the dominating cost element. The unit cost is about $500 million. Next slide, please. This shows us that the direct operating cost will be about $1.5 million per year, with recovery costs being the largest factor. And that concludes the cost analysis of SpaceShipTwo.
From the analysis presented, it can be seen that both vehicles are able to perform the desired mission and they are economically feasible for the space tourism market. A list of the main literature utilized by each discipline in this analysis is available upon request. This has been the StarQuest end of semester presentation. Thank you.